the equation. It is not the x-axis, which a lot of people thought it was. But if you looked at the front, there was no y on there. It was d, l, and lambda. So we're going to create an equation to relate x to all the other variables that we tested in class. So we have a couple of other variables. We have lambda is wavelength. Who tested wavelength? There are two couple groups. What kind of relationship did you guys find? A direct relationship. So this one was a direct relationship. D is known as the slit spacing. Who had the three windows? What kind of relationship did you guys find?
Inverse.
Inverse. And then L is our other variable, and that is the screen to the slits. So who had that one? What kind of relationship did you guys get? You got direct. So what we're going to do, what I wanted to do it before the end of the hour yesterday, was take everybody's data, put it all together, and create the equation that you guys are going to use. It's one of two equations that you're going to use. So I want you guys, the bottom of the lab is create an equation. X equals what? Well, x has to be directly proportional to wavelength. It has to be directly proportional to the distance between the screen and the slits. And it has to be inversely proportional to this. So, shh, don't yell it out. Talk to your neighbors. Come to a consensus, and then you're going to pick. Huh? You don't like your neighbors? Are you pointing at them like, I don't like that kid, that's what I got to work with? Ian's like in an island in no man's land. Alright, don't talk to Kelsey, she knows the answer already. Alright, Tristan, what do you think?
X equals lambda times L divided by D.
Anybody have anything different? Because we had in the afternoon, we had a couple groups that were, well, we had one group that was different.
That's not the right answer. Is that someone's guess?
Well, let's look at this. This is what Tristan just said. So does this follow everything over there? If lambda is directly related to x, that means as one goes up, the other one goes up. If this goes up, does that go up? Yeah. Same thing with L. There's a direct relationship. So if L increases, we should see an x increase. Is the equation set up to do that? Yeah. Inverse means it needs to be a part of a fraction. It's in the denominator. Meaning if one goes up, the other one goes down. So if the distance goes up here in the denominator, the overall answer decreases, yes? So this is a form of the equation that you're going to use. I just rearranged the variables when I write it out because that's just how I memorized it. So this is what physicists did. They tested different variables, they graphed it, they found the relationships, and then they put it all together and made an equation. Okie dokie so far? Are you going to be able to see if I turn out the lights and use laser pointers?
I don't know.
Okay, we'll test it. We'll see.
Yeah.
We shall see.
You just put a little screen on the movie and said.
I know. All right, so if you didn't fill out the bottom of your lab, fill out the bottom of your lab, and then pass them up.
Chelsea, do you want mine too?
Are you going to be here 4th hour? Oh my God.
It's lots of time.
So this is like a, you get like double your money on this one.
Double my money.
Sort of, I don't know, is this going to work as like an assignment or?
No.
Oh, well then never mind. At least you get to be here and
Yeah. I do.
take notes.
I think he was, but I can't hear. Is that like a... So we're just going to make a final part? Yeah. Whole class. Yeah, it's like, we'll try and get like both.
Okay, so let's get started on notes. We'll come back to that equation in a minute. We'll identify all the variables. So, diffraction. We know that diffraction is the bending of a wave. Today is the 22nd. And
That's the way it was before.
You know, it's really bursting my bubble. All right, fine. Okay, so diffraction is the bending of a wave as it passes around a barrier. So, diffraction is just this part right here. I have my openings. The fact that the waves go in as straight waves, all in phase with each other, and then they're still in phase with each other, but they've curled as they go to the opening. Notice I only drew enough to see the bending. I didn't draw the overlap because that's something different that's happening. What you guys saw in the lab yesterday was actually two different things happening with waves. They diffracted as they passed through the openings, and then we had the overlap that created the constructive and destructive interference. So, if the diffracted waves overlap, then they will constructively and destructively interfere and create the fringe pattern that you guys saw. I don't know why they call it fringes, but that term has been used for a long time. So, on your homework, you're going to see a question like this, where it's going to have, those are awesome. That's like Clyde Ewell good. Okay, so then we're going to have, it's Clyde Ewell. You don't have to draw this, just pay attention so you know what to expect when you see the homework. This is really, really freaking good.
Homework?
The homework? God, what? It's the last homework assignment.
No.
So, if these solid lines are all crests, so from both sources, both openings, we have crests. In between the crests, they're going to be troughs. So on the homework, it's going to look like dotted lines for the troughs. Okay? So, we have points where we have crest and crest overlapping, and we have points where we have crest and trough overlapping. So, if you look, this is a dotted line, this is a solid line. So this point right here is a crest and a trough. So the dot is a crest and a trough, which means we're going to get what kind of interference? Destructive. And then we have a point right here, which will make a star. I don't know what kind of star that is. Or this one right here. Now this first star that I drew is a bold line and a bold line, right? So those are crest and crest. What about the one right next to it? Trough and trough. So those are going to be constructive. Now, for it to be constructive interference, that must mean a crest and a crest or a trough and a trough are coming together at the same time. So, how does that work in, where's my little demonstration? Here it is. Okay. So let's say I have my double slits. What's actually happening? So I need somebody to come help me. Let's see. Aaron, come here. You're going to have to sit here. Normally I do it way over there, but it's going to have to be on film. You've signed the contract agreement? Okay, good.
Yeah.
Okay, so what I need you to do is, everybody sees that this is just the order stuff that elementary school teachers use.
Nothing up my sleeve.
Nothing up his sleeve. And these are both crests. Everybody good with that? Okay, and they are the exact same length. Okay?
Whoa.
So Aaron is going to hold his hands out like this and just hold the waves. So his hands are the sources of the two. They are basically the double slit openings. Okay? So what's coming out of each slit will be a crest. And I need a lab stool. Here, hold that for me for a second. Okay. So, turn around. All right, hold one in each hand, like shoulder width apart.
You don't fall.
You're not gonna fall. Okay, so you have wide shoulders. Okay, so we have crests and crests right here. At both ends there are crests. So coming together in the center, if they both travel the same path length, we have crests coming together. But if the path lengths change, so in the lab yesterday you guys saw a central dot, yes? But then you saw dots on either side. So why did you see dots on either side? Because some of the light, not all of the photons travel to the center. Some of them could go sideways, which is why we get this big arc. Some are going this way, some are going this way. So when they overlap, do-do-do-do-do-do-do, and I hold them back that way, hold them tight. What do I have here? Right here and here. I know it's hard to see. Is it crest and crest?
Yeah.
How different are they in path? What do I have this left over here? A whole wavelength, right? So I will get constructive interference, a whole wavelength off, and then if I go another shift over, how much wavelength do I have now? 2 wavelengths. So to have constructive interference on either side, like this, or like this, or like, it's harder to do as it gets tight. I will have at least whole. So happy I have immature children in my class. Are you 6th grade boys? Because girls don't like 6th grade boys. Okay, so to have constructive interference, it has to be a whole wavelength off. What about destructive interference? What do I have there? I have a trough and I have a crest. They have to be half a wavelength off all the time for destructive interference. Thank you very much. Okay, so for constructive interference, the path length must differ by whole wavelengths. Now this means the path length from the 2 slits. So from the 2 openings, or the slits. So that path has to differ by a whole wavelength. So we're still getting crest and crest lined up, but they're not traveling the same distance. Okay? For destructive, how much do they have to differ by? Half? Could I have 2 halves?
Yeah.
No, because that becomes a whole wavelength, right? Could I have 3 halves?
No.
Yeah. So for destructive interference, the path length between, or from, sorry, use the same wording, from the 2 slits must be 1/2 wavelength difference. And then we'll put or 3 halves, 5 halves, 7 halves. We can't have an even number because that turns it into a whole, which turns it into constructive interference. Okay? Everybody good so far? Is this kind of making sense? Silence means I guess so.
Mm-hmm.
All right, so this experiment is called Young's double slit experiment. We did it well before there were lasers, in the 1800s. and saw this happen, that this destructive interference happened. It was not what they expected to happen. So what Young's double slit experiment was, in Young's double slit experiment, the screen, sorry, not the screen, there were two slits, cut with like a razor, cut them into a film, and the film back then was not a nice plastic coating. It was paint a piece of glass black and take a razor blade and slice it in two straight lines. And then they didn't have lasers. You couldn't do this with a laser pointer. Use sunlight coming in through the window and have the diffraction pattern. What was expected? What do you think he expected to see on the screen? Two lines. He expected to see this on the screen. What he saw, so what he observed, everybody who did the lab yesterday without the three windows, so the wavelength people and the L people, what did you guys see? Did it look like this on your screen? Did it look like this on your screen? It looked like this, right? And then we had more kind of out here, which I will show you. I'll get the lasers out in a minute. Okay? That is what the double slit actually looks like. So you expected to see this coming from our sunlight, passing through our double slit grating, coming onto the screen, thought we'd see this, did not, saw this instead. This is what is expected if you think that light behaves as a particle. Reflection is an example of light behaving as a particle. The photons hit the mirror and they bounce off. Angle of incidence equals angle of reflection. You can play pool and do the exact same thing. This was what was expected if we thought that light was a particle. This is what we see because light is also a wave. Problem is, they can't behave as a wave and a particle at the same time. It's called wave-particle duality. So you either can be one and have characteristics of behaving as a particle, or it can have characteristics of behaving as a wave, but it can't do both at the same time. So this is called wave-particle duality. And the double slit experiment is the foundation. It's the #1 experiment to prove that light behaves as a wave. There's a couple of other experiments in modern physics that do this, but there are far more that explain it as a particle. Okay, so in the double slit experiment, this center one right here is called the central maximum. Maybe we'll draw, do you guys need this bigger on your paper? We can make it bigger. I might. It's totally fine if you need it larger. We'll make it bigger. Oh my gosh. There's a lot of drawing in this particular chapter. So we have the double slit. Looks like this. So we have our center. It was actually maybe a little bit brighter than the outside fringes, though you may not have noticed that. Especially if you had, like, I think the red laser doesn't differentiate very well. So we have 4. There's actually more. We don't need to draw all of them. And then we had another set of fringes on the side, like 3 of them here and 3 of them here. This thing right here is called the central maximum. The central maximum is where, when Aaron was sitting here and holding these border pieces, when they traveled the exact same distance from his holding them up to the center up here. So when the path length from each slit is the same, that's the central maximum. So the path length from, I can spell, from each slit is the same. That's what the central maximum is. So this right here, this one and this one, are where the light traveling from one slit is a little bit longer than the light traveling from another slit. So therefore, this is what we call the first order. And then this one here is the second order. And then the third order. So the orders are positions of constructive interference where the light from one slit travels a wavelength farther than light from the adjacent slit. Okay. It's a lot of definitions. It's all going to come together. Multiple slit works the same way. So we're going to see double slit and multiple slit. Like another group had 100 lines per millimeter, 300 lines per millimeter, 600 lines per millimeter, not just 2. So they had far more spacings. Did your pattern look like this, you guys who did the 3 windows? Those people who did multiples, don't write this down yet. Those people who had multiples, their stuff spaced way out, yeah? And then you had another one where maybe they were closer together, but they were far easier to observe, and this didn't look anything at all like this, okay? Those of you who did the double slit, I know that there was one group that they couldn't find where the double slit was. Remember I showed you that the double slit looked like that, and I told you put your laser beam right there. People were putting their laser beam right there. And the people who were doing that wound up seeing single slit, which I will talk about probably tomorrow. It looked like this. It's basically this pattern, but instead of having all these little fringes, they're big blobs. Okay? But we're going to talk about why this happens tomorrow. Hopefully you are here tomorrow. All right, is everybody good so far? This is doing okay? All right. All right, so let's go through. I want to demonstrate stuff when I know more people are going to be here, so I think I'm going to do the demonstration stuff tomorrow. Let's go through one of our equations. So we have this equation that you guys derived yesterday and today. All it is rearranged. You guys wrote it down on your lab as x equals lambda L over d. This is how I was taught. This is how you see it most of the time in textbooks, and so we leave it this way. The reason why it is this way is lambda is usually a constant. When you're doing an experiment, your wavelength is usually like, okay, we're going to use this laser pointer, that's a constant. dx and L are things you can control. Well, x is the end result, but d and L are things you can control also. So let's label things, first of all. Lambda is the wavelength. You will see nanometers. So how do we change nanometers to meters? Times 10 to the what? You guys remember?
9.
Negative 9. So you are going to have to do some converting on your own. D is the spacing between the slits. L is the the distance between the screen and the slits. And then X is our fringe spacing. X is what got projected onto the screen. So the distance between each of these is the X. That leaves us with N. What the heck is N? It's on the board, guess. Think about it this way. If N is a whole number. If it goes from 1 to 2 to 3 to 4 to 5, what variable over here am I going to change? Would I change the distance between the slits? No. Am I going to change how far apart those two things are? No. Is it going to change X? Yes. Are there different X positions? Yes. So N is called the order. N for double slit and multiple slit. There's a rule that goes with this, and it's the opposite for single slit. We're going to do single tomorrow. So, for double and multiple, the N has certain numbers. We saw that to have constructive interference, and I wrote it right over here, I said constructive has to be off by whole wavelengths. Yes? So, to have constructive, N has to be whole numbers. So what do you think is going to happen for destructive? To have destructive, I have to have a what and a what arriving in the same place at the same time. A crest and a trough. Crests and troughs are off by how much? Half a wavelength. So to have destructive interference, N has to equal 1/2, 3/2, 5/2, 7/2, on and on and on. So let's label some things here. Let's draw them out because you need to know what are all these different things, not just by definition, but visually, what was happening? So, we're going to draw the lab. Laser pointer. What variable is the laser pointer? Wavelength. Then the light beam hits my screen. And I have slits on my screen. My screen is, this is terrible. This is up higher. Okay. So the light hits my screen. What is this distance right here?
D.
Out of all those letters?
D.
D. So the spacing between these two slits is what D is. Okay? Then the light, when it passes through this, is going to project out, and we're going to get interference, and it's going to create this pattern here on the screen. Oh my, this is just terrible. I'm very not. I have to do this well. It's terrible. Okay, so on my screen, I get this. Now, there are two variables that I need to plug in here. What is this distance from here to here?
L.
L. What is this distance from here to here? X. So the distance between each dot is X. Hopefully you looked yesterday and noticed that those spacings are all equidistant. Yes? Unless you had it at an angle and you could project it out, you could get the outer edges to be a different distance away. Now, if I look at the spacing between adjacent dots, what's the N? So, let's go over here. If we know the spacing between adjacent dots, fringes, sorry. Meaning, I know, let's say, here's the central maximum, here's the first order here's the second order, here's the third order. If I know the distance between these two, so let's say that this x is 3 centimeters. What is the n from here to here? Between 2 and 3. What do you think? How many orders away? How many orders separate the two of them? How many orders separate 2 to 3? 1. If I know, conversely, if I know a measurement from the central maximum, so let's say that I have, here's the central maximum, how many orders do I have? This is tricky. The pattern is symmetrical, so do I have 8 or do I have 4? 4. So this is 1, 1, 2, 2, 3, 3, 4, and 4. So if I know that this distance from here to here is, let's say, 32 centimeters, the x in this case is 32 centimeters, and the n is what? 4. What if I were going from here to here? If I say that this x is, I don't know, like 21 centimeters, what's the n? 2.5, right? Because I'm at a destructive interference position, and destructives occur on the halves, and I'm between the 2 and the 3, so that tells me the n here is 2.5. Does that make sense? I might phrase this, I might not give you a picture like this on the test, but I might say the third bright fringe. So if I say the third bright fringe, n is 3. If I say the third dark fringe, 1, 2, 3, n is 2.5. Does that make sense? Tristan?
What is the 32 centimeters?
I just made it up. Like I said, what if? So let's say this is what was projected on your screen. Let's say we measured these. They're just numbers I pulled out of my head. Okie dokies. Does this make sense so far? Everybody okay? What do you think happens to the brightness of these dots as we go further out?
They get dimmer.
They get dimmer, right? Because the light, as it passes from my double slits here, so here's my screen with the double slits, the shortest path is the central maximum for both of them. So we're going to know that that's the brightest. But then when we go from here to here, and from here to here, this one over here on the right has to travel a longer path length by a whole wavelength. And so because they're traveling longer distances to get further out, the intensity drops off. So what this looks like, if we were to graph intensity versus order for a double slit, so what this looks like, we have to have equal sides on the x and y, or on the y-axis, because the pattern that we create is symmetrical. So what we create on the right is also going to be what we create on the left. This is intensity here on the y-axis. This is the order on the x-axis. So our orders are just going to count off 0, 1, 2, 3, 4, on and on and on. We're not going to do that many. Where's the brightest? The central maximum, right? So this would be the central maximum right here. And then we're going to have first order, second order, third order. Okay. Mr. Drillish is doing something interesting. All right, so there's my central maximum. Very, very bright. But then notice how far it goes down. Does it go all the way down to 0 intensity? Did you see black spacings between each dots? You didn't see a little bit of light, you saw no light in between each dot, which means the intensity has to drop off all the way down to 0. Then we're going to draw the first order. Should the first order go as tall?
Nope.
No, it was not as bright, though to the human eye you might not have noticed. And the first order we have to have on both sides because the pattern was symmetrical. And that also goes all the way down to 0 because the intensity is 0 where there's destructive interference. We should get no light happening. So this is first order right here. Then we draw another one. Second order. And again, the intensity is tapering off because the path lengths are longer as we go out. And we could do the third one. We could keep going forever and ever if we wanted to. How far out could we spread this light? Because this light was projecting out onto the whiteboard. Is there a limit to how far it can go?
Yes.
What angle is the limit as to how far it can go? So let's think about this. My laser pointer is pointed directly this way. 12? 12 degrees.
12.
Okay. 90. Somebody used their brain for their answer. So we have laser pointers going straight, and I have first order, then I have second order, then I have third order, then I have fourth order. Eventually, is my arm going to go out to 90 degrees?
Yes.
My laser pointer starts out this way. It's going to diffract, 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 till we get to 90 degrees. Then you can't diffract anymore. That's the farthest that it can go. It can't go around backwards.
Over 90 plus 9.
But look, it does this. It's not going backwards around. Because these are the slits. This is the opening here. So it can't go behind the grating. Does that make sense?
No, that looks like 180 degrees to me.
It can go this way. How far can the light go this way? The limit that it can go is out to 90 degrees. It can't go, it could go straight, right? So I could have light go straight through the slit, hit the central maximum. I could have first order, second order, third order, fourth order, fifth order, sixth order, seventh order, eighth order, ninth order, 10th order. As I keep going across the screen, how far can this screen go? So much so that this angle that it projects out, it keeps projecting out, is 90 degrees. It can't go backwards on itself. I know what you're saying, isn't this way also 100 degrees? But we always go from the central maximum either to the right or from the central maximum to the left.
Okay.
Okay? But yes, I get what you're saying, the scope of 180 degrees. Okay. So we'll get to angle in a second because there's an equation that goes with it. Really, there's so much to do. Okay, so I wrote multiple here. Multiple slits are better. The more slits you have, so multiple slits are called diffraction gratings. The more slits you have, you get more diffraction and interference. And so therefore, you get more information. So a single slit experiment, all that it's ever really used for is to take light that, maybe you have a beam of light that consists of lots of crest, lots of trough. They're not in sync with each other. And you want the light that goes into your experiment to all be in phase, all the crests all together. So it blocks out all the other things. We'll talk about single slits, I said yesterday, or earlier. We'll talk about it tomorrow. But with double slit, we saw that we had two opportunities all the time to diffract light and then interfere it, and we got a pattern. If we then went to triple slits and then quadruple slits, what will happen is this pattern that we saw, like this, these dots will start to break apart. So this will become 1, 2, 3, 1, 2, 3, 1, 2, 3, and we'll start getting more and more information out of this. Because we have more diffraction, more interference. What I mean by more information, not like a computer. You guys looked last year in chemistry, remember looking at the neon and the hydrogen gas tubes? Did you guys look with little tubes to see a whole bunch of stripes?
Yeah.
Those things are diffraction gratings. With lots and lots and lots of slits, it allows for each wavelength that's in neon has a different X. Does that make sense? In hydrogen consists of 2 violets, 1 cyan, and 1 red. They have very, very specific wavelengths. So the diffraction grating allows them to separate to specific positions. So if you were going to be a chemical engineer or a mechanical engineer, and you had to identify different materials, you would use a spectroscope to figure that out. If you were going to go into biology and do some things with like body fluids, and you have to do, let's say, some type of, let's say you have to do urinalysis on it, on urine sample, and you need to find out what's in it. Then you use things like this to help break down the different compounds and elements that are in there because they give off specific patterns. Okie dokie. So how do we deal with this multiple slit thing? Let's say that we have 600 slits per millimeter. I need to know how far apart each slit is. So we need the distance between each in meters, not millimeters. This is one where you're going to have to convert units and make sure everything is in meters. You can't leave something like lenses and mirrors. We could keep everything in centimeters. But this time, everything has to go to meters. So we're going to finish this part up and then we're going to do an example, okay? Tomorrow we'll do the single slit and we'll do some other demonstration stuff. We need to get a couple problems done. So, how do I figure out the distance between the slits? If you had this as a lab yesterday, don't answer. I realize it's first hour and half of you don't answer anyway. If I need to know how far apart each slit is, do I need the distance in the numerator? Probably. Okay, so what I first have to do is invert this. In 1 millimeter, there are 600 slits. So this now will tell me how far apart they are. But it will tell me that answer in millimeters. So what do I have to do to this? Convert millimeters to meters, yes? So what number goes in the denominator? If I put millimeters in the denominator, what number has to go there? How many millimeters are in a meter, boys and girls? 1,000. So 1/6 is 0.167, and then this is 10 to the 5th, but it's in the denominator, so it's 10 to the negative 5th, or 1.67 times 10 to the negative 6 meters. This is our D value for multiple slit experiments. Okay, so this is how you deal with multiple slits, because I'm not going to tell you how far apart they are. I'm going to tell you there's 600 slits on the screen. I'm going to tell you there's 13,000 per inch. That's a lot. That's so much so that you can't see them with the naked eye. All right, we're going to do an example, and then I'm going to be done. Okay.
That's always going to be D.
That will be, if for multiple slits, that will be how you get D. If it's a double slit, I'll just tell you how far apart they are. Okay? Okay, so let's do an example. Do you guys want to do a double or a multiple? Double, okay. So, What color laser?
Orange.
What? We had 3 colors yesterday. Yellow, or yellow, not even yellow. Green, red, and violet.
Yeah, yellow.
Green.
Cyan.
I'm picking.
Brown.
Clear.
Black.
So the green laser pointer has a 532 nanometer wavelength. Shines on a double slit where the slits shines on double slits. I can't write properly. Where the slits are, let's say, 1.2 millimeters apart. The interference pattern, the fringe pattern, is projected onto a screen that is 1.8 meters away. So part A, how far apart are the fringes? And then we'll do part B, where is the second dark fringe? We can get this done and then that's it for today. So our givens, we know that the wavelength is 532 nanometers. So what do we have to do to that?
10 to the negative
10 to the negative 9. So this means we really need 532 times 10 to the negative 9 meters. Okay? We don't have to worry about proper scientific notation because we're just going to plop that number into the equation. This information right here, 1.2 millimeters. That's how far apart the slits are. What's that variable? D, X, or L?
D.
D. So 1.2 millimeters means we need that in meters. Move the decimal how many? 3 backwards, so 0.0012 meters. Then we know that the screen is 1.8 meters away. What is that? Is that X or is that L? L. Remember that you observed X in the lab. So we don't have to do anything with this. It's already M. So, part A, I just want to know how far apart is each fringe. And then part B, I want to know where's the second dark fringe. So let's do the first part. We have dx over L equals n lambda. For the first part, what are we going to make n? Because I want to know the distance between 1 and 2, or 2 and 3, or 3 and 4. N will need to equal 1 in this case. Okay? So if I'm solving for x, I can ignore the n, really, but I'll have n lambda times L and divided by d. So we wind up with 1 times 532 times 10 to the negative 9 times L, which was 1.8, all over d, which is 0.0012. So, of course, it's not anything I can do in my head. These are just crazy numbers.
12.
It's not 12. Is that your lucky number? How could it be 12? There's a 10 to the negative 9 in there.
12. I just did the math, it's 12.
Did not.
There's 12 in the denominator, so.
I know, you should be happy there's a 12 in the denominator. 7.98 times 10 to the negative 4 meters. So So 7/10 of a millimeter. Really small. Okay, so they're really close together. Let's look at the last part. Where's the second dark fringe? So the second dark fringe, the central maximum, here's 1, here's 2. If this is the first dark fringe, this is the second dark fringe. What's the end? 1.5. So you do the exact same situation, but the n becomes 1.5. So you can take that answer and multiply it by 1.5. And you get 0.001197. So 0.0012. Oh, there's your 12.
There it
Damn.
is.
Whoa.
Okay, so I did that fast because I want to pass out the homework because the bell is going to ring. So I didn't set it up. I apologize.
We knew 12 was the answer. If I don't get it before the bell rings, I'm not gonna get it.
Yep, that's the.